Hello, this is a demo for the presentation that I'll be doing on Thursday. It's currently 4:30 a.m., so I might not present with the most energy and the most enthusiasm as I would on presentation day, but I just wanted to give a demo of what I'll actually be saying and what the slideshow contains. So just have faith that I'll be more energetic and better at presenting with hand movements and walking around and stuff on the actual presentation day. I still have a day to practice. I just want to make sure that the timing is right and then make sure that the content is good with you, professor, whoever else is watching. So yeah, let's begin. Good afternoon, everyone. Thank you for joining me today. My name is Jeremy Key. I'm a third-year undergraduate at the University of Virginia, presenting on the behalf of my research group, FloodWatch. Our group focuses on building early warning and flood monitoring systems for vulnerable communities. We emphasize practical and scalable solutions, and as part of that effort, we leverage remote sensing, particularly synthetic aperture radar in this paper, along with other modalities such as on-ground IoT sensors and weather data, specifically rainfall, along with crowdsourced imagery. So this paper today will talk about how we can leverage synthetic aperture radar to improve the quality of our flood predictions. More specifically, the goal of this paper was to develop a nationwide ward-level flood susceptibility score using synthetic aperture radar. And we want to fuse that with rainfall data to have a flood risk prediction for the entire nation. So to give some context on why this problem matters before diving into the details, is that Vietnam is one of the most flood-prone countries in the world. During monsoon season, extreme rainfall can overwhelm entire local drainage systems, leading to rapid flash floods across the entire nation. And in the south of Vietnam, low-lying regions like the Mekong Delta, which is typically at or below sea level, has moderate storm surges that can damage entire infrastructure and cropland, displace entire communities, and put lives at risk. So a few hours of early warning would make a huge impact, and that's the role that FloodWatch serves, is to provide that type of situational awareness. So despite the clear need for solving this problem, predicting floods is hard. To know when and where flooding occurs is something that's super important, and pretty much rare, extreme, highly localized bursts of rainfall that actually produce flooding. It don't follow predictive seasonal patterns. And furthermore, even if you could predict the rainfall, two places that receive the same amount of rainfall may receive two completely different flood outcomes depending on that terrain, soil usage, hydrology, etc. And additionally, flood reports in Vietnam are sparse, delayed, and inconsistent, as this makes it very difficult to train supervised models to do this flood prediction for us. So our paper focuses on two nationwide signals that we can obtain consistently. The first being rainfall, which will serve as our temporal driver, tell us when flooding will occur. And the second is SAR-derived vulnerability or susceptibility, to tell us which wards are likely to flood on any given day, and that will serve as our spatial driver. So I think the most logical place to first start off at is to talk about rainfall, the temporal driver. So as I mentioned previously, rainfall in Vietnam is driven by extreme rainfall events like typhoons or monsoons or any high rainfall event, and not the typical day-to-day rainfall. So we really care about the tail behavior of our rainfall distribution in any given ward, not the average. So in order to model the tail events, we'll use extreme value theory to create a distribution that represents these extreme days. So the way we do this is we extract a rainfall time series of every ward in Vietnam, and we create some type of dynamic threshold at which once rainfall goes above this threshold, we mark that as an exceedance, and we fit all these exceedances into generalized Pareto distribution, which then represents all the extremes for this ward historically. So now we can answer the operational question on any given day, this amount of rainfall in this ward, how rare, how extreme is it? This will give us our first baseline score of flood susceptibility or flood risk on this day. We'll also construct an unsupervised linear rainfall baseline model to compare against this EBT model. I'll talk about in the findings later. So secondly, rainfall alone can't tell us the whole story, as it doesn't encode other features that lead to flooding, such as river connectivity, like the hydrology, etc. So SAR is a nationwide signal which provides a consistent time series that we can leverage to have some sort of spatial awareness. So we use synthetic aperture radar, specifically Sentinel-1's C-band, as it operates day and night and it can see through storms. This is really important as we want to know how the landscape reacts against floods. So the main idea is that we use VH polarization, which is vertical transmit, horizontal receive. We send signals, we send out a pulse, and we receive backscatter against rough surfaces like soil or vegetation. And in our image, that appears as bright as the measures get reflected back to the antenna. Whereas once we reflect the radar signal to open water, it reflects away from us, leading to a dark image, suggesting that we can analyze the surface of the land, seeing through storms. And we can analyze the signature to determine when certain pixels become temporarily inundated. So we need to make sure that we're actually analyzing the surface and not just the signal alone. So we need to run our SAR images through a standard pre-processing pipeline, which first we take our image and do radiometric calibration to sigma not to it, which essentially means we want to have some sort of meaningful backscatter value for that can be compared across a time series. Second thing we do is we use terrain correction to account for our viewing angle and also like steep hills or mountains, and remap our values to its on-ground location. And the last thing we do is we speckle filter to account for radiometric interference of the wave return to make sure that we're actually extracting data about the surface and not just random signal noise. So once we have an image that we can analyze, for every pixel we create a time series of its backscatter values, and we keep track of its mean and standard deviation. And once we have days where the pixel goes above, say, 2 standard deviations, we mark that as a potential flood day. So once we have potential flood candidates, as we've created like a normal signature for a given pixel, we mask out open water, steep angles, and we account for noise to ensure that our flood candidates can actually be pixels that have been temporarily inundated. And this gives us pixels that we believe are flooded for any ward on any given day. So once we have the time series of flooded pixels, we aggregate them to the ward level by counting all the total flooded pixels in a given ward's administrative boundary. And then we create a time series of the total flooded pixels. So for every ward, we calculate its baseline total flood pixels. And then on days where the total pixels become anomalous, so much higher than some certain threshold, we say the ward flooded on this day. And knowing which days have flooded, which days the wards have flooded compared to the total passings, on the days we are allowed to build a prior from there, either a monthly or a seasonal prior, to say how likely this ward is to actually flood. So now at the ward level, we have a rainfall EBT model that can give us a flood risk score based on the rainfall alone against a ward's histories of rainfall. And also we have a ward susceptibility score, which tells us how likely a specific ward is to flood on any given day. So we fuse these two scores multiplicatively to have one final daily flood risk score. Now this makes sense as rainfall is our temporal driver, and only on days where there's extreme rain can it flood, and only in locations where it's actually vulnerable to flooding will it actually flood. So this approach is interpretable and it makes sense. But how do we evaluate the quality of our model before we actually deploy it? Well, like I stated earlier, in Vietnam there's a pretty big problem where flood reports are coarse, sparse, and inconsistent. So what I mean by that is the specific dates a flood occur are pretty inconsistent, maybe somewhat delayed, along with where the flood actually occurred. We don't have polygons. So I think the best we can do is have some sort of knowledge of which province it actually flooded in. And that's not granular at all. Another thing is that sometimes floods may not get reported at all, and people have different definitions of a flood. So someone may consider a small flood a flood, while someone else may not consider that a flood at all. So because of this, we need a standard evaluation pipeline. And our approach is we gathered all government reported floods and put it into a data set. We marked these as 1, and because flood days are very rare, like I'd say 1% of days, we also negatively sample non-flood days in the same orbit and in the same ward to balance out our evaluation data set. Then we expand all of these floods and non-flood days by an end day window, say 2 days before and 2 days after the recorded dates, to account for some sort of noise. And once we have this, we have a province level binary label on if this ward flood or on this province flooded or not on this day. But we have ward level flood susceptibility scores. So what we do is we max pool, or we take the highest susceptibility score of a ward in any province and use that as the province's total score. And then we now compare that score against the binary flood label. We compare our entire data set, and we use 2 metrics to track the quality. The first metric is AROC, which is a risk scaling score. So how separated are the flood days from the non-flood days based on score? And the second one is calibration, or Brier score, which is pretty much a mean squared error of the binary label compared to the flood risk score. And so the results of our experiments, well, the first one is that our extreme value theory model is well calibrated compared to a linear model. So it has much more confidence in predicting floods over non-floods. And this is expected. But one small problem is that the AROC is lower. But I feel like this makes sense, as because floods have many different definitions, like a small flood may be considered a flood. Extreme value theory really only cares about the most extreme values. So it may disregard a small flood and not consider it a flood and give it a score of 0. And this is a problem. But a good thing is, what's exciting is that our spatial priors actually solve this problem. As when we fuse our EVT model with the spatial priors, the AROC becomes the same level or better than the linear model, and encodes some sort of flood vulnerability. And it also improves the calibration, our Brier score. This is great. Another thing we notice is that monthly priors perform better than seasonal priors. This can be explained by saying monthly priors have a more fine-grained like definition. So they can keep track of seasonal patterns better, as it might pick up on monsoon timing, irrigation patterns, or land usage. Seasonal priors would smooth this out and not pay attention to these small details. So some of the limitations of our work is that Sentinel-1's 6-day revisit period has temporal gaps. So it might miss the peak of some floods, or it might miss entire floods. That's a big problem, But one thing that we can do to fight against this is we can use other sensors or other satellites to keep track of the susceptibility scores. We can also use on-ground IoT sensors to make up for that revisit period. Another thing is that we can use our on-ground IoT sensors to validate our flood pixels to see if there was actually flooding there and to make sure we're not producing false positive flood pixels. So to briefly wrap up and summarize our work, what we contributed was we made a nationwide, a SAR-derived flood susceptibility score for every single ward in Vietnam. And we also created an extreme value theory rainfall distribution for every single ward in Vietnam. And we learned that when combining these two, we can greatly improve the quality of our flood predictability. In theory, we could apply these priors to any type of model, maybe a state-of-the-art deep learning flood model, and use it as a feature or something. So this is really good for research, but it is also very useful to our platform. Furthermore, we created an evaluation framework for giving us like a numerical baseline of how good or how well our models performed in a data scarce region like Vietnam. So once we validated our quality of our model, we'll deploy it into our FloodWatch platform, which we've already done. And in the long run, like I said, in our future work, we'll use it with IoT sensors. So our FloodWatch platform is always open to working with new people, new collaborators, whether you're in the IoT, machine learning, or remote sensing field, or any other field. I believe that this problem is a humanitarian problem, and we'd like to get as much help as we can. So the more details and further explanations are displayed in our paper. Thank you everyone for your time, and I'd be happy to take any questions. Yeah, so I went like a little bit over time, but it's also like 5 a.m. I feel like I'm really tired and I'm pretty thirsty, so like I'm slurring my words a bit. But I hope this was clear. Again, I have another day of practice, and I just wanted to show you what I have so far. I'm not looking at a script at all, too. So yeah, thank you.